All right, welcome everyone to the Maui Institute for Astronomy. I'm Dr. J.D. Armstrong. Oh, I like that response. Right, we got cheering in the background here. I am Dr. J.D. Armstrong. That wasn't a suggestion for cheering me. I'm the Maui Technology Education and Outreach Specialist here, and one of the things I get to do is put together these talks and invite interesting people like Jerry Isdale to come and speak to us. So a little bit about Jerry, and of course everyone knows I get to make lots of mistakes. I've upped it from one mistake. Jerry is the founder and now head instigator for the Maui Makers, and for those of you who do not know who the makers are, they make stuff. They're very into tech, 3D printers, you name it, but anything to create and make new things. He was a longtime software engineer, also a farmer, and he is now the holder of the DARPA SpaceGAMBIT grant, and he'll be talking to us about all the fun things going on with the NASA Asteroid Grand Challenge.
Yes.
I even did that one right. That's scary. Hey. All right, so let's give a welcome to Jerry.
Thank you. A quick note here. JD is doing a really wonderful job of scheduling a whole lot of stuff. And so next week, Friday, we have Dr. Gary Davis coming to talk here as well. So come on back next week, Friday. You can miss First Friday. And come on down here for the fun stuff at this talk. This is the continuation, the British astronomy here over there. Anyway, enough of them. That gonna work? Nope, that didn't want to work. Fine. Slideshow. First slide. There we go. The Asteroid Grand Challenge. This is actually was supposed to be an animated GIF, but it didn't want to work that way. That's their real logo. The Asteroid Grand Challenge. NASA has started a number of programs they call the Grand Challenges. The first Grand Challenge is the Asteroid Grand Challenge, but in all, the Grand Challenges are basically a call to the general public around the world to help out, come up with ideas and solutions to various large problems. They're not looking for a solution, they're looking for a whole lot of small ones, because it's such a big problem to try and solve. The asteroid issue is one of them. The Asteroid Grand Challenge, which was announced about a year and change ago now, was to find all the asteroids that threaten human populations and to know what to do about them. The little URLs at the bottom there are available later. So first of all, what's an asteroid? Some of you probably know this by heart, some of you may not. An asteroid is sometimes called a minor planet. There's a lot of changes about what an asteroid is or was in the last few decades. It used to be that asteroids were hard, rocky things and comets were icy snowballs, and now they've sort of said, well, sometimes comets are hard rock and asteroids are icy snowballs. So basically, they now look at them as pretty much asteroids are stuff that's in the inner solar system that isn't a planet. That is my definition, not any official NASA one. They're generally hard rock, but they are, some of them are solid, and some of them are actually pretty puffy, soft things. They range in size from about 600 miles in length to dust particles. And their orbits are quite variable. Or the orbits themselves of each one is varying in differences. Some of them are out past Jupiter and stay there. Some of them cross inwards. Some of them are within Earth's orbit. Some of them loop around in these little strange orbits. But a lot of them cross the Earth's path, and that is the problem. Sorry, I hit the button too many times. A couple of pictures of asteroids. Gaspera, Ida, and Matilda, they look like your classic big rocks in space. They have these lovely colorful images. And then this one here Itawakas? Sir? Thank you. This one is a classic pile of rubble. This is what a lot of the asteroids look like. It's just a bunch of rocks, the elemental things that were the universe, the solar system, as it kind of started accreting, and the rocks made up themselves, and then they got together and they broke up, and then they made more. So it's just, you look at it, it's a pile of sand. It looks a lot like what a bulldozer driving across the field in Maui would kick up. And interestingly, on this one here, this picture was taken by a Japanese satellite spacecraft that approached really close to it and got some really nice pictures. In some of the pictures, you can actually see motion, or the sand and the rocks sliding downhill towards the center of gravity. It is still changing its shape, which is one of the reasons why you don't blow these things up. Why are we talking about asteroids? Because they could be a big threat, and because they're full of all sorts of wonderful things that we could use. A lot of good resources. There are somewhere over 600,000 asteroids known, and we are seeing them, asteroids happen. I'm going to try and play a video here. We'll see if this will work. First of all, we have to get a cursor back. Whoop. It's not going to give me a cursor. Wow, it's one of these wonderful things. Now that's the wrong one. Come here, you. There's the puppies. Darn it. Aha! There it comes back. Now you're not going to be able to hear this one very well, but this is a animation of the asteroids as they were found since 1980. Down in the corner here, you might be able to see it saying 1982. You can see as slowly as the four inner planets are running around. There goes the Earth there. The red line asteroids in here are the ones that are within the Earth, and out here you can see as they find more of them, they light up white as they first find them. Generally, when if you notice, they're white. They're out over here somewhere, that away from the sun, because that's where we look for them. We can't really look at the sun and see them very well. We burn up our telescopes doing that. 1988, things start getting a little bit faster. We start seeing more assets start coming online. 1990, interesting correlation here to the end of the Cold War, when more assets became available and certain assets came online and people started paying a bit more money to it. 92. A lot of the time the observations happened and we discovered them because they were looking at something else at the time. They got a whole bunch of pictures and they looked at them and, well, and behold, there were some things in there that moved. And here we have more and faster in the late 90s. As the asteroids start picking up more, we have more assets coming online, more or better software for analyzing the images. You can see now the green trail. That's the asteroids as they've been found. The ones in the red are Earth crossing. And it gets faster and faster in 2000. And then there's a couple of moments in here where you see them show up in some diametrically opposite ones. There's a lot of asteroids out there, aren't there now? But The interesting thing is there's a lot of empty space out there because the scale of this is pretty darn small. Yes, it's mostly in the plane of the ecliptic. There is a couple of other animations I found of this that you can see that there is an interesting toroid, that there is a fair bit of variation off the elliptic. And here in 2011, 2012, it gets pretty darn dense.
I see with these new ones, the white ones that show up, and as it sweeps by the region of Jupiter, when it gets to Jupiter, you don't see any right there, and then you see them show up on the other side. At least that's what I got from that.
It looks like it. There may be something
Jupiter doing to it.
Repeat questions and comments from the audience so that people in the virtual world.
in the virtuals. Hello out there in the virtual worlds. Yes, I'll stand up in a moment. And I'm going to try and play the second video here. And I'll put the mic down near this one here. This is from a group called
Nuclear Test Ban
B612.
Treaty Organization monitors the Earth around the clock, listening for the infrasound signature of nuclear detonations. Between 2000 and 2013, this network detected dozens of massive explosions in our atmosphere. But not a single one of them was caused by a nuclear weapon. The actual cause, asteroid impacts. Between 2000 and 2013, there were 26 recorded asteroid impacts on Earth, ranging in energy from 1 to 600 kilotons. For comparison, the nuclear bomb that destroyed Hiroshima in 1945 exploded with an energy of 15 kilotons. While most of the asteroids shown here exploded at too high an altitude to cause damage on the ground, they do remind us that asteroid impacts are not rare. An asteroid large enough to destroy an entire city hits the Earth on average once a century. Because we don't know when or where the next major impact will be, our current strategy for dealing with asteroid impacts is blind luck. But we can change that. An early warning infrared space telescope for tracking asteroids would give us many years to deflect an asteroid when it's still millions of miles away. The next great space mission is protecting the planet. Join us.
B612 is an interesting group, and that video has caused a little bit of controversy because B612 is a private foundation that wants to put a satellite in an orbit around Venus that will give us the ability to look in places where we can't look from the Earth, where we may be able to see asteroids that we otherwise would not find. And in particular ones that are coming at us really quickly from the direction of the sun, and we might be able to prepare one way or another. But this video about the number of asteroid strikes came out earlier this year, caused a fair bit of controversy within the Asteroid Grand Challenge and my friends at NASA. The B612 guys did not clear it with NASA ahead of time. Or they talked to people and so forth and was like, no, don't talk about that. Apparently what they did is, if you caught it, they were using the nuclear detection system, which detects large airbursts, or would detect large explosions. And over the past decade or so, it has come up with a whole lot of these large explosions. The most rational explanation for them is they are large meteor strikes. So these are happening a lot more often than people were thinking about. So how do we find or detect asteroids? Well, the basic way that we find them is we take lots of pictures of the stars, take pictures of the same stars fields in succession, and you look for things that move. In this one here, it's a still image, a longer exposure image. So, and the one thing here, which is a little bit stretched out, is kind of blurred. It says, oh wait, that's not a single dot, it's a line. So that's an asteroid or something moving in your field of view. Over here, this is a series of several images that are stacked up, and you can see this one little thing moving in the images. This one here is taken from the asteroidzoo.org site, which is a very interesting site. The Catalina Star Survey has made all their images, or a large portion of them, available to the Asteroid Zoo. And the Asteroid Zoo is asking citizens to go out there and look at the images. And they show you a set of 4 images, and you say, does anything move in here? Yes, no. Does it look like it's an asteroid? Is it an artifact of the cameras? They have a little bit of a nice training thing in there. So it's an attempt to get the general public working on the asteroids. You may be familiar with something like the Galaxy Zoo and some of the other citizen science astronomy programs. Same organization that's doing it. This time it's the Asteroid Zoo. Some of you are intimately familiar with the Panstarrs device, the Panoramic Survey Telescope and Rapid Response System. This is the premier instrument for finding asteroids. It happens to be located just up the hill from us, and the guys that are running it at this beautiful setup over here is upstairs. If you haven't seen it, some point in time, come back for the open house and see it on the wall upstairs. There's some beautiful pictures that show the cameras it has. It has what was, maybe not anymore, but was the world's largest digital camera. And upstairs you can see some of the early pictures from it that show you what a regular camera would be and the size of the image and the amount of stuff the amount of pixels in there is phenomenal. It sends down about 1 terabyte of data every night. It sends it down by truck. They don't bother shipping it down. They put it on a disk and take it down by car. At least that's my understanding. That is a picture of Panstarrs, and hopefully there'll be more of them out there sooner or later. How many of you have actually been up there and seen Panstarrs personally? Does anybody here work on Panstarrs? Okay, cool. I know there was going to be a couple of the world experts here. The next thing after you've detected them, because Panstarrs finds them all, and Panstarrs reports the findings generally semi-automatically to the NASA Minor Planet Center. The Minor Planet Center is another highly underfunded NASA organization run by Harvard up there. I got to visit the guys. They have significantly less space than you guys have here. But they are a database of all the asteroids, all the minor planets sightings that have ever been made. They have these boxes of papers that came from decades ago, and now they have electronic systems where you can tie in on their, go into their database, find out what is visible from wherever you are, and try and make an asteroid observation with whatever telescope you have. Hopefully it's one that you can see. So you can find the telescopes and you do follow-up observations. If you can spot one, if you spot it where it is, you can, if you are authorized and accepted by the Minor Planet Center, you can send them a report that says, hey, I found it again, it's over here. They don't let most people send them reports about finding things because they would be inundated by all sorts of maybe good reports and a lot of probably bad reports. They have enough of the bad reports as it is right now, dealing with all sorts of postdocs and so forth that can't seem to get the right answers. But it's very important to have these follow-up observations that say, yes, we did find it here, or wait a minute, it was supposed to be here. I had everything set up right and I didn't find anything. Look, because then you say, well, the orbital calculations you had are wrong. There are a number of asteroids that they found that said, this one looks like our orbital calculations say it's going to hit the Earth. And we don't know where it is anymore. We lost it. Is it still out there? Did we have the orbital estimate wrong? So they've gone and they've looked at them to try and figure out where those are. Very important follow-ups. One of the best ways to find out what's going on is they did a couple of studies where they said, well, if it was going to hit the Earth, it should be here. They went and they looked and it wasn't there. So they said, it's a pretty good idea that that big asteroid is not going to hit the Earth, at least on the order we thought. So we'll have to try and find it again. Once we've found them a number of times, we can characterize them. Characterizing them is another very important step. What are these asteroids made of? How big are they? By doing what is called a light curve analysis, you get the amount of light that comes from an asteroid or from the star over a period of time. You see it vary a little bit, and you can say, okay, by its variations, it's rotating and reflecting, and you're hopefully getting the right albedos off of it, so you know that it's got a good idea of how reflective they are. Some of these are very dark objects. They don't reflect a lot. They're also using radar. NEOWISE was a satellite system that was doing some radar. We also have done some very good, humanity, has done some really neat radar studies of asteroids using a couple different really nice devices. And spectrometry is another very important aspect to find out what it is that we're seeing coming back from what's the light that's coming back? What is it made of? What brands, what types of light? Even in the X-rays and infrared, you can use all these different spectrums to find out what the materials are that the asteroids are made of. Then we can figure out if it is something that's going to hit us. Is it a big hard rock? Is it a big pile of water, frozen ice? Don't know. You may also find from the spectrum that it is made of something very interesting to go and look for. So which is something that some of the other people are using to go and chase them down to say, we want to go to the asteroids and make some money out of them. We'll get to that later. A big thing is using access to large telescopes. Half meter or more is what you pretty much need to see most of the asteroids that are out there. Asteroids are generally the ones except for the real big ones, they will have a magnitude of maybe 19, 18 if you're lucky. So you need a fairly good-sized telescope to see them and to collect enough light to catch them. There are a few out there. Some of you may be familiar with the Las Cumbres telescopes, and those work nicely. I was able to do an asteroid observation mission here, right about in that room, right over there, with JD last fall, using one of the Chilean telescopes. We got online with his system. He walked me through what they have to do to find the targets in the MPC database, which is not a simple thing. And then we made a couple of observations, and I had an amazing bit of beginner's luck. The first ones that we saw was an asteroid that had been reported first time by Panstarrs the night before. First 3 pictures we got of it were dead on, and JD's looking at it going, this doesn't happen. This does not happen. It's never this easy. First 3 we did. The second one worked kind of well, and the third one, the clouds came through or something, and they shut down the telescope for a couple of hours. SLU.com and iTelescope.net are remotely operated telescopes that you as a citizen can sign up and pay a fee, and will be able to use their telescopes to make observations. Most real astronomy these days happens by remote observation or rarely with the carbon-based sensors anymore. Everybody's using the cameras because you can do a lot better with them. SLU has just opened some new telescopes. iTelescope is getting some larger ones out there. Basically, you sign up, buy a subscription to them, and you can make observations and get really neat pictures out of their telescopes, not just of the star fields and the asteroids. You can go get some neat galaxy pictures and all those other things if you want. They do have some of the large telescopes coming online now. And then what do we do about them? As you remember, the Asteroid Grand Challenge is first to find all the asteroids that threaten humanity, and then know what to do about them. Well, we got a number of things. NASA has a mission in planning to capture the asteroid. And the European Space Agency has one they call Don Quixote. It's actually a two-part, a two-vehicle mission. Don Quixote had his sidekick.
Sancho Panza.
Yeah, Sancho Panza, which is the name of the first satellite which is going out there and doing the laser range finding and targeting, and then Don Quixote is going to come along and smack it with probably about the same results.
What kind of energies are we talking about in sizes? I mean, that's a very formidable. They're not really talking about deflecting it, right? Just
No, this is just
analysis.
it's an analysis, and is it feasible to have a deflection? There are deflection options, and I'll go to those in a couple. And then the other idea is to mine them or reuse them. There's a lot of really good resources out there. And the other thing we can do is we can just ignore them. But remember, the dinosaurs didn't have a viable space program. The asteroid capture mission, in March, they funded 18 different plans. 4 were for asteroid capture systems. There were 2 sets of rendezvous sensor suites, laser, radar sensor suites to put them together. 4 of them were for adapting existing spacecraft, or soon-to-be existing spacecraft.
What's for sensors or for assay?
These were for rendezvous. That was to try and say, okay, if we're going to be out there in the middle of space, we got to find this thing and target it, and to the point where we can actually get up to it and see it. We had studies of the secondary payloads and a few partnerships to see what they could do. Let's see if this one will. Come on, you. Oops. This is an animation from NASA on finding one of the asteroids. You see it targeting it with the laser. What they're planning to do is, one of the concepts is to bring a large bag and capture it in the bag. And then they suck all the air out of the bag. Not that there's any air up there anyways, but collapse the bag around the asteroid. And we got it nicely captured. Yeah, some sort of drawstrings, pull the balloon tight around it. And then once you've got it to that point, you can use your thrust here to pull it along. The idea being to pull it from wherever it was into some near-Earth asteroid. I believe they were talking about one of the Earth-Moon Lagrange points to stash it in. And then once they've got it stashed there, and here they got it nice and tight, fire up the engines, take it off over there, get it to there, and then we launch some rockets and send the humans out there to take a good look at what's inside. So, yay. Why humans?
Yeah, why not use robotics to do this mission? Since
You-
the asteroid is, and
You could probably use a fair bit to select your samples robotically. This perennial question of whether or not it's worth it to send robots or send people for the.
effective cost is far less when you have robots to do it.
Yes, but then you wouldn't have a reason for Boeing to build this beautiful space capsule.
Well, that's 2 better places to go.
The question there was why send humans? And here we have them. They walk out to go get it. We'll just run this one a little bit quicker. They can, make their samples, collect their samples, and bring them back to Earth.
Have we
Yay.
already done that?
Not for an asteroid.
That
We did a comet.
Which is essentially the same thing.
Not necessarily.
Well, it is. It's just a different kind of mass.
Yes, so is the Earth.
And again, the feasibility thing, the ability of this depends on the mass of the object. Remember, the people in the video can't hear your question. Okay. Your comments. I mean, it seems that the amount of energy required to do it with large, massive asteroids is enormous. So this must be for basketball-sized asteroids. Is there some mention of that in this program?
This is for fairly large asteroids. Well, not fairly large, a couple of a dozen meters across. Anyways, there are a variety of different ones that they're looking at to capture. They want to get something of a reasonable size so that they can get a bunch of different samples, different parts of it. I don't have all the details on that one. I'm not. But the next question is when you're trying to deflect them. There are a dozen different ideas out there right now, and NASA is looking for more ideas. Some of the current ideas, there's your basic kinetic impulse techniques. Go up there, strap a couple of rocket engines to them, and fire the engines off and push them out the other way. Explosive propulsion, some way of exploding things on the surface that pushes them off or makes them move. Impact propulsion, hit it with something really hard. And then one of the ideas is to hit it with another asteroid. You have one in low Earth orbit, use some small rockets to push. You find a big one that's a planet killer or something, and then you just redirect that small one to hit the big one. Play billiards with them. Some of the more interesting ones, if we have more time, this is the key part about detection, if you have only a couple of years or a couple of months, then you can try one of the ones that gives a high delta V, change the where the asteroid is coming in its orbit, just enough to miss the Earth. That's a miss is great, just a little bit of a miss and we're fine. You hit it, not good. But if we have decades and we know that this one's probably going to hit us, but not for another 20, 30 years. Well, we can go for one of the slow push ones, strapping an ion beam engine to an asteroid. Ion beams fire a bunch of ions off. They're really lightweight pulse, but it's enough, if you keep doing it, that over time it will be enough to deflect the asteroid. Remember, the Earth moves its own diameter in about 5 or 6 minutes, so it doesn't take a lot of distance that you have to change in order to miss. One that I like kind of cool is what they call the gravity tractor. Gravity tractor says, you got a big asteroid out there, you just stick a smaller spacecraft near it, and just by the fact that it's sitting there nearby, it's got its gravity, and it moves a little bit here, and the asteroid will get perturbed a little bit and follow along. Just by being nearby, it moves it just enough to not hit the Earth. Another idea is to use a solar sail, which would collect a whole lot of sunlight, point it at the asteroid, and boil off a little bit of the asteroid. You heat it up enough on that side, and then some of the material boils off, and that creates propulsion, pushes it away. The simple solar winds by themselves are enough to push the asteroids and change their course, which is one reason we need to go back and have more follow-up observations to make sure that they haven't changed their course. Painting the asteroid, another thing here is using multiple lasers or other types of solar collectors to light the asteroid up, and simply changing its surface albedo, the reflectivity or absorption of it, give it some sort of a paint, and maybe it'll move it just enough. These are all theoretical ideas. One of the interesting ones that was mentioned to me a few times by a number of people, this is a NASA NIAC study. It says we can do a hypervelocity asteroid impact using an NED. An NED is a nuclear explosive device. This is not we're going to land on it and blow it apart. Blowing apart an asteroid doesn't do you a lot of good. All you wind up with is having grape shot hit you rather than a cannonball. Maybe it's better, maybe it's not, depends on how small you can get them. The idea here, though, is you do a double tap. You send a lead satellite in that comes in, makes a small crater. The small crater gives it a nice little dish area here. You follow in with your nuclear device, and you set off a big impulse power, and that pushes the asteroid a lot further. So as far as the impulse techniques goes, this one has probably some of the best chance of succeeding, with its general caveats there. Mining and reuse. There are two large corporations, or corporations that are highly backed, Planetary Resources and Deep Space Industries, which have both announced commercial missions to asteroids to go and harvest them. I believe it was Planetary Resources, which has been talking about going out there and harvesting the platinum and bringing back all the platinum. If they can harvest one platinum-containing asteroid, it probably has more platinum in it than the rest of what we have currently on the market, which would do wonders. It would be worth trillions of dollars until you calculate in that you now doubled the amount of material, and so its value has dropped dramatically. My personal opinion is, why do you want to bring this stuff back and drop it back down the gravity well? We're trying to throw stuff out of the gravity well to begin with to get ourselves into becoming a spacefaring civilization. These things are made up of really good materials to use for building stuff. You could, this picture here is an idea where they would have a harvester, which is melting the asteroid parts, taking out all the different vapors and turning them back into the metals, and constructing a space station or a spacecraft of one form with them. Another interesting idea is to not bother harvesting them like this, is just hollow out the asteroid and use it itself. The asteroid gives you an awful lot of shielding material. And shielding material can be very, very helpful out there because you got all this radiation that you don't have a Van Allen belt to stop. Yes. So if you've got a couple kilometers worth of asteroid and you can leave, a quarter of a kilometer of rock, beats trying to make steel out of it and then make a quarter kilometer of steel. So just use it as it is. And then you could always just plain old ignore them. But as I said, the dinosaurs didn't have a space program, or at least they didn't have an effective one. We don't know for sure that they didn't have they may have had a highly sustainable, organic-based civilization that just rotted away and left no trace. But they got wiped out by a big asteroid. There's another one out there that sooner or later will hit the Earth. We need to find it first. JD mentioned SpaceGAMBIT. This is a quick overview of SpaceGAMBIT. I am the contract holder, the grant holder for SpaceGAMBIT, which is officially known as the Hackerspace Space Program. We were funded by DARPA for 2 years at $500,000, $250K a year, to encourage maker projects that promote humanity's long-term survivability and expansion into space. Real nice, broad spectrum thing. We got a lot of mileage out of it, and habitats and biotech and a lot of interesting projects the first year. This past year, we hooked up with NASA with a Space Act agreement to collaborate with NASA on the Asteroid Grand Challenge. We signed it in February, and in June we signed off on 10 different contracts. We funded 10 contracts to mostly in the area of promoting education and awareness of the Asteroid Grand Challenge. There's a couple of video games. There is some money going to some of these telescope networks to make them easier to access, get more public access. There's a asteroid hackathon coming up. I believe it's in October. We're going to have it to make it to develop a better, more user-friendly interface to the Minor Planet Center, so that the general public, or the citizen science and the intelligent part of the general public, can get better access and do more fun things with it. And there's we also have at least one project here on Maui, back in the corner back there. Ben and Gudra are doing what's called the Asteroid Response Center, which is an information kiosk, a touchscreen system which is going to be displayed at a couple of venues later this year. And that will be the end of SpaceGAMBIT. That's the end of our 2-year run, and we've had a great time doing it. But then I get to go back and work on my farm. If you want more information, that's my email, isdale@gmail.com. You can go to spacegambit.org and find out more about SpaceGAMBIT. agcnotes.wikispaces.com is the semi-official wiki setup of where all the notes on a lot of this information is buried in there. And this lovely one here, the nasa.gov mission_pages/asteroids/initiative, is where you'll find out about the overall asteroid initiative, which is both the Asteroid Grand Challenge and the Asteroid Capture Mission. So if you have any questions on that or anything else, go ahead and ask me questions now. This is the end of my official talk. Sir?
So what exactly is the Grand Challenge?
What exactly is the Grand Challenge? The Grand Challenge is to find all the asteroids that threaten humanity and know what to do about them. So they've been having a lot of different events happening around it. They've have several different large seminars. They put out calls for papers. There have been at least 2 or 4 large seminars on it where people brought in papers. There's a site called Top Coder. Top Coder is a contest group that says, hey, we got a challenge here, a programming contest. They have a number of contests they're running on Top Coder for people to create programs, software programs that will process images better, to control satellites, control telescopes. I've forgotten exactly what all the Top Coder challenges are, but NASA's put a bit of money behind it. There's some prizes for those different types of challenges. We're funding these 10 different little projects, not using any NASA money. We're using DARPA money. And we have some telescope automation projects, the informational ones, and that sort. So there's a lot of different thrusts to the overall Grand Challenge. They have in the wiki, you can find a lot of the different seminars and the papers that they've had. All the papers they do have, the sessions are broadcast in NASA live streams. They've had a lot of outreach to students. There are a couple of middle schools around the country that have participated in asteroid hunts and gotten time on some of the different telescope networks.
One of the teachers that did that is here.
Well, one of the teachers is here has done that. Thank you. Does that give you an idea about what the Grand Challenge is?
Yes.
Hopefully. Thank you.
My son here actually worked with Mr. Today on that asteroid.
Excellent. The son back there worked with the teacher, Mr. DeVay. Thank you. It's a fun little project. Finding them is a neat bit of science. Sir.
I see a lot of activity in the location or finding, describing, and characterization of these objects, and a lot of activity associated with this detection and description. But I don't see any connection in any of the programs to actual hardware that we could use in order to perform a deflection or a delta V of some kind. All this stuff is out there, and it seems to be to get the astronomers and the people with money connected to each other. And I don't see any follow-up thing, the actual follow-up hardware. For instance, what if we found a low albedo object and it was going to strike the Earth in 4 months? We'd be caught here with our pants down because there's no hardware available. There's at some point we need a connection between all this activity and some means of doing something about it. So I'm not seeing any of that in the last 2 talks I've seen. And are you aware of any? So the question is, are there any solid programs for deflection?
Yes.
Beyond studies.
The trick is there are plans on the table, on the drawing board to do deflections before they're actually doing deflections. I mean, this one, the NIAC plan here, this one,
I've seen it.
This is a plan which is fairly well along, and he knows how to do it. They obviously have not built one of these. Getting a hold of a nuclear weapon and all that is not something that's easy to do.
Well, that's easy. There are plenty of them out there.
Right, they're out there, and you could probably get a hold of one if it was...
But you have all this other hardware that you need in order to make it happen, especially if you're going to actually have a contact type explosive.
Right. That's where there are the projects that NASA funded earlier this year, back in March, and there is buried under this. Nope, it was